All right, let's compute another one of these definite integrals using our summation formula. So I want to compute the integral from 1 to 5 of 2x squared plus 4 dx. All right, so let's see, delta x is b minus a over n. B would be the top bound, so that's a 5 in our case. A would be the bottom, that's a 1 over n, that's 4 over n. And then xk would be a plus k delta x. So in this case, that would be 1 plus k times 4 over n. All right, so we want to compute f of xk separately and simplify it, so we don't have to carry the entire summation while we're simplifying. We get to write a bit less this way. All right, so our function is 2x squared plus 4, so if we apply it to xk, we get 2xk squared plus 4. Our xk is 1 plus 4k over n squared plus 4. All right, so I'm going to need to expand this. I'm going to need to expand the 1 plus 4k over n. I'm going to expand it so that I really can simplify the sum neatly into sums of k, sum of k squared, sum of 1, and so on. So here I'm going to get 1 plus 8k over n plus, and then I square this part. So it's always the same formula. A plus b squared is a squared plus 2ab plus b squared. And so I need the b squared at this point. That's going to be 16k squared over n squared. And I'm going to have plus 4. All right, so what I'm getting is I'm getting 32k squared over n squared. I'm getting 16k over n, and then plus 2 plus 4, I'm getting plus 6. All right, so that's my function f of x squared, f of x, k, and then I want to compute Sn. So that's going to mean summing delta x f of xk. Delta x is 4 over n, and then f of xk, we simplified it already. It's 32k squared over n squared plus 16k over n plus 6. I'm going to multiply this n, the 4n, I'm going to multiply it in. Then I'm going to split it until I get the sum of k squared, sum of 1. Okay, so I can apply my formulas. So if I multiply it in, I'm going to get 128 k squared over n squared plus 4 times 16 is 64 k over n, 4 times 6, n squared, n cubed. Don't forget you have an n here, I kind of missed it. And then 4 times 6 is 24 over n. We can split this. I'll get a summation of k squared. I'm going to get 64 times the summation of k plus 24 over n summation of 1. Right, so I'm getting 128 n cubed. Now I'm going to replace these sums by the formulas that we have. So that's n plus 1, 2n plus 1 over 6. I have 64 n squared, n plus 1 divided by 2, and then 24 n over n. And as usual, I have n squared in 3 terms, so I'm going to match each of the terms above with 1n. Same thing here, I have 2 terms and n squared. I'm going to match them, and these will match. And so what I'll get is 128 over 6, and then I'm going to get 1, and then n plus 1 over n to n plus 1 over n. And then I'm going to get 64 over 2, 1 times n plus 1 over n, and then I'll get 24 times 1. All right, so now I'm ready to compute the limit. So 128 over 6, that's 64 thirds. And then let me write these like we did in the last problem. I'm going to divide this and this. So I'm going to get 1 plus 1 over n. Same thing for the next term. I'm going to take this plus this. I'm going to split the fraction. So that's going to give me 2 plus 1 over n. And then the limit will be very easy to take. Same thing for the next term. I get 32, 1 plus 1 over n plus 24. All right, if I evaluate this, this goes to 2, this goes to 2, this goes to 1, this goes to 1. So what I get is I get 64 thirds times 2 plus 32 plus 24, and I calculated it beforehand, and that simplifies to 296 thirds. All right, so if we graph this function, we'll get something like that. And we got the area from 1 to 5. We got this area right here. We got that there was 296 thirds. All right, so let's write a recap of this. So when you want to evaluate an integral like this, especially if f of x is a polynomial, what you'll need is to calculate first, well, you determine a, b, and f of x. That's not too hard. That just means reading from the integral. And then you calculate delta x. Delta x is b minus a over n. And then xk is a plus k delta x. So you compute what these are. And then you write what f of xk is, and you simplify. And I would recommend that you simplify until you have a constant times k squared over n squared, a constant times k over n, a constant. So you have split it up as much as you could. Then you would find and simplify Sn, which is k equals 1 to n delta x f xk, and again I would simplify it until you got to a point where you have a number sum of k squared, a number sum of k, a number sum of 1, and then you would replace the summation by the summation formulas that we have, and then you would simplify. So you replace the sum of k squared by n times n plus 1 times 2n plus 1 over 6, you replace sum of k by this, you replace sum of 1 by this, and then you simplify a bit. You simplify until you get something whose limit is clear, and then you compute the limit. And that number that you get, that's the definite integral of f of x on the interval a of b, and it represents the net area of the region between f of x and y equals 0 from x equals a to x equals b. All right, in the next section, something very exciting is going to happen. At the end of it, we'll be able to compute this integral super quickly. So one thing I'll do then is I'll look at exactly this integral that we've just computed using, I would say, a whole page. I mean, I had a bit less than a page, but I was squished at the end, so a page of work, and we'll do it at a snap of a finger. Okay, but that's going to take a bit of work. That's when we'll have the fundamental theorem of Cal.